Let's look at some examples of using familiar linear algebra ideas in the context of general vector spaces. So for example, let's look at some examples in P sub n. Remember, P sub n is the collection of all polynomials with degree less than or equal to n. Okay. So what is a basis for P sub n? Well, if you think about polynomials of degree n, right, there's going to be some coefficient times x to the n plus, and then there's going to be some other coefficient times x to the n minus 1, and so on, all the way down to some coefficient times x plus some constant term. And right, any scalar, any real number could go in these positions. So what this looks like now is, it looks like it's just a linear combination of x to the n minus 1, and so on, all the way down to x and 1. Okay, so these vectors, they clearly span P sub n, right? Every polynomial of degree less than or equal to n is a linear combination of these polynomials. So I guess to have a basis, we just need to know, are these polynomials linearly independent? So are they linearly independent? Well, let's check the old-fashioned way. Take a linear dependence relationship, let's say a n x to the n plus a sub n minus 1 x to the n minus 1 plus, and so on, down to a sub 1 x to the 1 plus a sub 0 x to the 0, which is just 1, and say this is equal to 0. And this 0 over here is the 0 polynomial. So what we need to figure out is, are there any non-trivial linear dependence relationships? Well, the only way for two polynomials to be equal is if their coefficients are equal. So if this polynomial is equal to 0, that means a sub n is equal to 0, a sub n minus 1 is equal to 0, and so on, all the way down to a sub 1 is 0, and a sub 0 is 0. But that means we have the trivial linear dependence relationship. So the only linear dependence relationship here is the trivial one, and so these polynomials are linearly independent. So this is a basis. So it's not just, they don't just span P, they're a basis for P sub n. All right, well, so what is the dimension of the P sub n? Now that we have a basis for P sub n, we just need to count up how many elements there are in this basis. So for P sub n, how many things are there? Well, there's 1, 2, 3, 4, and so on. You can see that these numbers that I'm using to count are always 1 greater than the exponent, the corresponding exponent on x. And that means when I get to the end of the list here, my counting number is going to be 1 more than n. So it's going to be n plus 1. That means there are n plus 1 polynomials in this basis, and that means the dimension of P sub n is n plus 1. All right. Great. So that's kind of how basis and dimension works out for P sub n. Let's look at an example of a linear transformation. Let's show that the derivative is a linear transformation from P sub n to P sub n minus 1. So if we have a linear, to check if this is a linear transformation, I guess first we need to check if you take the derivative of a polynomial of degree less than or equal to n, do you get a polynomial of degree less than or equal to n minus 1? But yes, that's clearly true, right? If you have some coefficient times x to the n plus lower degree stuff, when you take the derivative of this, right, the power rule makes this n times whatever that coefficient was times x to the n minus 1. You see the degree has gone down by 1. So the derivative is a function from P sub n to P sub n minus 1, but is it a linear transformation? Well, let's check. Suppose we had two polynomials, say P1 and P2. If we take a linear combination of them like this, is it true that this is the same thing as a times the derivative of P1 plus b times the derivative of p2. Is that true? Well, it is true, right? These are just the familiar derivative rules. So the sum rule for derivatives says that we can split this derivative up at the sum. So now we have derivative of a times p1 plus the derivative of b times p2. But then the constant multiple rule for derivatives says we can move these constant multiples outside. For this to work, it is important that these scalars are constants, right? So it's the fact that these are constants that lets us move these outside the derivative. Otherwise, we'd have to use the product rule instead. So the derivative satisfies the characteristic property of linear transformations, so it is a linear transformation. All right, well, if it's a linear transformation, what is its kernel? So the kernel is, right, what we're asking is, for which polynomials, p, when you take the derivative, do you get 0? Well, hopefully this is a familiar enough question from calculus that you remember p has to be a constant. So the kernel, I've run out of room, the kernel of the derivative is just the collection of constants, right? Constant polynomials, that is degree 0 polynomials. This tells us in particular that this collection of polynomials is a subspace because it's the kernel of a linear transformation. Also, this subspace is clearly one-dimensional because it's the span of just the single polynomial 1. So the nullity of the derivative as a linear transformation from Pn to Pn minus 1 is 1.